Now we're going to see what happens when we apply work to a specific scenario when we have gravity affecting us lifting a crate up to a ledge. You'll see why we're looking at this scenario in a little bit. So we have a ledge. It's over here. It's 2.00 meters high, and it is 10.0 meters away from us. And we would like to take this box and get it up here. And we're going to look at two ways to do this. In the first way, we're going to pick the box up and then move it over. Okay, and we're going to calculate the work done by gravity in order to do this. Why are we looking at the work done by gravity and not the work done by us? Well, the main thing we have to contend with in order to look at the energy we have to put out here is the work done by gravity, right? So if gravity is doing 1,000 joules of work, we are going to have to do at least 1,000 joules in order to get the box over here, plus any additional work caused by friction and air resistance and stuff like that. So we are going to have two steps of the pathway here. We're going to have this part, which we'll call W1, and we're going to have So I'm not going to go back and record all that. Let's just look real quick here. So this is the 10 meters. This is the 2 meters up. Here's the box. We want to get it up onto the ledge. Here is W1, which is the part where we're going straight up. And here is the W2, which is going over the sideways. So we're going to look at those two parts. So remember, the equation generally for work is W equals FD cosine theta. And the force that we're looking here is weight, because let me make sure we're doing a capital W. The force we're looking at here is weight because that's the force of gravity, right? When we're near the surface of the Earth. So we're going to look at the work on this part. So work 1 is force of gravity on this box. So that's mg. How far up is it going? Well, that's the height, h, which is the 2 meters. And what is the cosine of theta? Well, we are picking the box up, but weight is pointing down. So that's cosine of 180 degrees. And so all of that is going to be a negative mgh, which is equal to, we can plug in our values if we want a specific number. And so that's going to be negative 32.0 kilograms. Again, pretend all those are 30 sig figs. 9.80 meters per second squared times, well, we already have the negative. So 32 times 9.8, which is 300. I forgot the 2. There's an h is 2 meters. So 627.2 joules, and we have a minus sign out front. Okay, and then what about W2? Well, we are going sideways here. So we have M and G. We have, if we could call this L, is the sideways part. It's L. But what's the angle? Force is pointing straight down. We're going sideways. The angle between those is 90 degrees. So we have cosine of 90 degrees. What's cosine of 90 degrees? It's 0. So there's actually no work being done by gravity during W2. Gravity is not helping or hurting the motion of that box during that segment. That might seem weird to you, right? Because it seems like you are still having to do a lot of work in order to get that box over there, right? But imagine it like this, right? If you had a frictionless track and you manage to shove the box across that. Even just a really good set of ball bearing rollers, right? And shove the box across that. Gravity wouldn't help or hurt the box rolling across that. There still might be other things like friction or something, but gravity wouldn't contribute to that. So that's why W2 is 0. Whereas gravity is definitely making it harder for you to get the box up to that path. So the total W for part A is this part, this negative 627.2 joules. Now we're going to look at another part, another strategy, which is building this ramp. So we're going to have the length of the ramp and the angle of the ramp, and we're just going to take the box and just take it right up the ramp. Right? Well, obviously we can do a little trig to get this. D is going to be the square root of h squared plus L squared. We're going to slightly overdo some sig figs here. Actually, it comes out to 10.20 anyway, meters. Oh, I put the square root after I already took the square root. Okay, and then theta is going to be the arctan of h over L. And that's going to be 11.31 degrees. Again, we're slightly overdoing some sig figs to make a point here. We could actually do all this exactly, but it's fine. Okay, so we want to calculate this work all in one shot going up this ramp. So the work is going to be FD cosine theta. We know the amount of force, it's the weight of the box, it's mg. We now know the distance, it's that hypotenuse. Now what is the theta we put in? Well, we found this theta, but that's not the angle between this ramp and gravity, because we have this extra 90 degrees, and gravity is pointing straight down. So we're going to take our 11.31 and add 90. So we have 101.31 degrees. So let's plug in all of our numbers. So we have 32 kilograms times 9.80 meters per second squared times our 10.20 meters times our cosine of 101.31 degrees. And we plug all of that in, and we're going to get 9.8 times 10.20 times cosine of 101.31, and we're going to get, well, almost the right number. When we round down to 3 sig figs, we get 627. If you do this exactly with trig identities, you will find that these are exactly the same. They're not just about the same. So why are these the same? It turns out it doesn't matter which way you get from down here to up there. You could go up and then over, or over then up, or up at an angle, or up, over, down, over, up, over, down. Any way you want to go, it's going to take the same amount of work done by gravity to get there. So, why calculate all of this trig stuff when we just have to do mg times the height it took, right? All we really need to know is how high it was when it started and how high it was when it ended. So this is the notion of calculating potential energies. When you have certain types of forces where it doesn't matter how you get from the starting point to the end point, those forces are called conservative forces. What that means is they are path independent. Those are synonyms: conservative forces, path independent forces. And all you have to do is find their starting point and their end point, and then you can calculate the work done by those. And we no longer usually call that work. We usually get rid of the work side of the equation and bring it inside as a potential energy. So instead of making this a negative outside, we're going to make it a positive inside. Notice this looks a lot like the opposite of the W that we had on the right side of the equation. We're going to have it as a positive on the left-hand side of the equation. So this is called gravitational potential energies. The energy an object has because it's a certain height above what? It's above whatever you want it to be. It's above your coordinate system. So when you're doing a problem like this, you're going to choose your coordinate system, and y is measured relative to that coordinate system. Doesn't matter what you pick for y as long as you're measuring everything in that system relative to that origin. So this is UG. Delta UG is equal to mg delta y. And it's usually the delta that actually matters when you're calculating something. So real quick, we have a 2 kilogram book and it's being lifted by 1.5. What's this change in potential energy? So we're calculating delta UG. So this is going to be mg delta y. So that's going to be 2 kilograms times 9.80 meters per second squared times the change in height. So we need to make sure we're getting the sign correctly. It's increasing by 1.5. So this is going to be a positive 1.5 meters. And so 2 times 9.8 times 1.5. So it's 29.4 joules. And then technically I only gave you 1 sig fig, which is certainly not what I meant to do. So however many sig figs you think I want you to write down there. So how do we actually solve a problem using potential energy? When you're solving a physics problem with energy, the first thing you're going to do is draw a picture of the initial and the final configuration. So just where everything is, right? All the physical objects, where they are. But you have to put a coordinate system down. And now you know especially why. It's because the potential energy is going to depend on what that coordinate system is. You're going to assign variable names for everything, like what the y's are, what the v's are. You're going to have an initial and a final to everything. If there's more than one object, they all have to have different subscripts. It's not usually the case in the energy problems I'm going to give you, but it could hypothetically be the case. And you're going to write down values for all the known quantities. So you're probably going to know one of the y's and maybe one of the v's or something. You're just going to know some of this stuff. You're going to start with the first law of thermodynamics, delta E equals W. You're going to fill in all the energy types and transfers you'll need, like the delta K and the W. And I need to emphasize something here. So let me get my... When we have the delta E equals W, these are external forces. Okay? Now that we have delta UG, gravity is now an internal force. We do not want to calculate work done by gravity. Now that we have gone through that example and have discovered that gravity can be counted with a gravitational potential, we are not also going to count it as work. So this is going to be anything else. So if there's a fan pushing on it, or if there's friction, or if there's someone pulling on it with a rope, or something like that, those are going to be external forces on your system. But gravity is no longer external. In fact, we have to technically include the Earth in our system as the agent that is causing the gravitational force. That's a technicality, it doesn't really affect how you do the problem, but that's what's happening there. You're going to put in equations for all the energies you know, like the equation for kinetic energy. You're going to solve for whatever unknown variable you have, plug in known values with units, solve for the final value. So let's do an example. This is a very likely type of example that you might have on a quiz or homework or exam. So you have a flat road with a frictionless board, and you're going at 13 meters per second. You go down a hill, and you end at the end of the hill. So there's your board, and you're standing on the board, and this is 7 degrees, and this length is 22 meters, and that's what you want to figure out. Now, we have seen other ways to do this. We are going to calculate it in an energy context. So our VI is equal to 13 meters per second, and we want to find VF. Notice we have no M. Okay. We need to have our coordinate system. It is convenient to put your coordinate system so that the origin is at the lowest point you will ever go. So let's put it right there so that the bottom of the hill will be at 0. Let's think about the different kinds of energies we're going to have. So are we changing speed? Yes, so we need a kinetic energy. Are we changing height? Yes, so we'll need a gravitational energy. And is there any external force done on the system? The only external force, since there's no friction, is work. The only external force is the normal force. What does the word normal mean? It means perpendicular. Remember, that was the math word for perpendicular. That's where it gets its name. So, if the normal force is always perpendicular to where the object is moving, what is cosine of 90 degrees? 0. The normal force doesn't do any work. There are no other external forces. So our energy is conserved in this problem. There's no work being done. Energy will transfer back and forth between kinetic and potential. So we have Kf minus Ki plus UgF minus UGI is equal to 0. And we are trying to find the final, so we can have Kf is equal to, we'll solve all this across, so we have Ki plus UGI minus UGF. Now, we have said that YF is going to be the one that we set to 0, so UGF will also be 0. By the way, this is a warning. If you look up some of these problems, you will see the erroneous statement that KF is equal to UGI. That is because someone has skipped some steps trying to set up problems. This is sometimes true in some problems. It is not always true. This is always true. This is how you need to solve this problem. So now we're going to plug in the equations for each of these. So this is 1/2 mvf squared is equal to 1/2 mvi squared plus mgyi. You can see that there's an m in every equation, so we can divide it out in every term in our equation, so the m divides out. We can work a little bit more. We can multiply by 2, so we have vf squared is equal to vi squared plus 2gyi. Be careful when you take the square root, because when you take the square root here, the whole term on the right-hand side gets the square root. Don't think you cancel out anything. Okay, that's it. That's the solution. So we're going to plug in the values we know. 13.0 meters per second, square that, plus 2 times 9.80 meters per second squared times, right. So what is yi? We didn't calculate that yet. So let's think over here. The hypotenuse here is 22 meters. This angle is 7 degrees. So y is equal to sine of 7 degrees times 22.0 meters. So we'll just put that in right here. So this is 22.0 meters times sine 7 degrees. So we have 13 squared plus 2 times 9.8 times 22 times sine of 7. We'll take the square root of that, and we get 14.9 meters per second. And this makes some sense with our intuition, because if you go down a frictionless hill, you would expect to end up going faster at the bottom than you started at the top.